Welcome to today's paper reading. Today's paper is titled, LLM Augmented LLMs, Expanding Capabilities Through Composition. This paper was published on the AR14 preprint by Rachit Bansal and colleagues from Google Research and Google DeepMind. The abstract introduces foundational models, which are large-scale models with billions of parameters trained on extensive datasets. These models exhibit significant capabilities across various domains. However, their monolithic structure poses challenges, making it both difficult and costly to enhance them with new skills. To address this, the authors propose COM, a method that introduces cross-attention between models to compose their representations, thereby enabling new capabilities. COM allows for the efficient scaling of large language models, LLMs, on new tasks by reusing existing models with a few additional parameters and data. Importantly, it preserves the existing capabilities of the models by keeping their weights intact and is applicable to diverse domains and settings. Large language models, LLMs, exhibit a variety of foundational capabilities, including common sense and factual reasoning, world knowledge, and coherent language generation. These capabilities have been leveraged to create domain-specific models with enhanced abilities in areas such as code generation, copy editing, and mathematical problem solving. The question arises whether these domain-specific models can be composed with an anchor model to enable new capabilities. For instance, can an augmenting model's code understanding be combined with an anchor LLM's language generation to facilitate code-to-text generation? This work introduces the Composition to Augment Language Models (COM) framework, which aims to effectively combine these models while preserving their individual capabilities. Figure 1 provides an overview of the COM framework, which aims to augment an anchor large language model (LLM) with new capabilities by composing it with specialized augmenting models. The figure illustrates 3 augmenting models, MA, with different capabilities: key-value mapping, low-resource languages, and code. The anchor model, MB, remains unchanged during this composition process. Additional parameters are learned over the model's layer representations to facilitate this composition. The leftmost plot shows a MA trained on a set of string integer mappings, such as x1 10, xn 2, while MB is a large language model with arithmetic capabilities. COM successfully composes these 2 frozen models to solve arithmetic tasks on keys that neither model could solve independently. Notably, COM demonstrates the ability to generalize to the entire key-value set, even when trained with arithmetic examples covering only 20% of the keys. In the realm of parameter-efficient fine-tuning, a significant amount of research has focused on introducing a small number of trainable parameters while keeping the original model unchanged. This approach, however, faces challenges when adapting models to new domains not present in the original training corpus. On the other hand, model merging techniques, such as task vector averaging, provide a way to recombine different capabilities of models, but these methods are only effective when the original models are well aligned. COM, in contrast, is more versatile and can be applied to any set of models. Additionally, the concept of model and task compositionality, particularly in modular encoder-decoder methods, has been explored to allow flexible reusability of different encoders. COM extends this ideology of model reuse and modularity to enhance the composition of capabilities in large language models. The COM framework aims to compose an augmenting model MA with an anchor model MB to enable new capabilities. This composition is designed to achieve a joint task C. The process operates under several key assumptions: access to model weights and intermediate representations, but no ability to alter these weights or access training data. The composition learning involves 2 main steps: linear transformations to align the representations of MA with those of MB, and cross-attention layers to facilitate interaction between the models. These steps are crucial for the alignment and interaction of the models, despite their weights being frozen. The cross-attention output is added as a residual connection to the layer representations of MB, which is then propagated through the remaining layers of the model. In this section, we present the experiments conducted to demonstrate the capabilities of our approach across 3 domains. Firstly, in the key-value arithmetic domain, we generated a repository of 25,000 key-value pairs and created arithmetic expressions involving these keys. 3 datasets were generated to evaluate the model's performance on key substitution, arithmetic, and numeric arithmetic tasks. Secondly, for low-resource languages, we used the Flores 200 dataset to evaluate translation performance, and the GSM 8K dataset for math word problems. The results show significant improvements in both tasks when using our composed model. Lastly, in the code understanding and generation domain, we evaluated performance on code completion, text-to-code, and code-to-text tasks. The composed model demonstrated improved performance across all tasks, highlighting the effectiveness of our approach. Table 1 presents the evaluation results of a synthetic key-value task, focusing on the accuracy of 3 models, MA and B, and their composition MA circle plus B. The augmenting model MA demonstrates high accuracy in memorizing key-value mappings, achieving 98.1% in the KV substitution task. However, it lacks arithmetic capabilities, scoring only 4.2% in the numeric arithmetic task. The anchor model MB, on the other hand, excels in arithmetic operations, with 73.7% accuracy in the numeric arithmetic task, but fails in tasks involving key-value data. The composed model MA circle plus B shows significant improvement, achieving 84.3% accuracy in the KV arithmetic task, effectively combining the strengths of both MA and MB. Table 2 presents the translation performance from low-resource languages, XX, to English on the Flores 200 dataset. The composed model MA circle plus B demonstrates significant superiority over both the underlying models MA and MB. Specifically, MA circle plus B outperforms the individual models in 175 out of 192 languages. Additionally, MNTL represents an enhanced version of MB that has been further pre-trained on DNTL, showing that the composed model MA circle plus B achieves comparable performance at a fraction of the training costs. Table 3 presents evaluations for grade school mathematics, GSM, problems across low-resource, LRL, and high-resource, HRL, languages. The data reveals that the COM model achieves substantial improvements in performance for both language sets. Notably, the gains observed in the HRL set indicate that COM effectively mitigates the issue of catastrophic forgetting. Additionally, the composed model MA circle plus B demonstrates superior performance compared to both the augmenting model MA and the anchor model MB across several languages, underscoring the efficacy of the COM composition approach. Table 4 presents evaluations for code generation and understanding across 3 tasks: code completion, CC, text-to-code, T2C, and code-to-text, C2T. The results indicate that augmenting code understanding to MB using MA significantly improves performances across all datasets. Notably, MA circle plus B outperforms both MA and MB in CC, P at 1, and shows significant improvement in T2C, P at 1. In the C2T task, MA circle plus B retains performance, and is marginally better than MB. The table also highlights that fine-tuning MB on decode leads to catastrophic forgetting in text generation tasks, whereas COM effectively mitigates this issue. Table 5 presents the comparative performance of COM, MA circle plus B, across various ablation scenarios. The metric hashtag MB indicates the number of languages where the model outperforms the base NTL model, MB, across 3 tasks. The table reveals a notable performance drop when specialized MA is replaced with vanilla or random variants, highlighting the importance of MA's specialization. Additionally, using MA solely as an encoder results in a significant decline in performance, underscoring the necessity of iterative decoding. Lastly, the table shows a considerable performance difference when comparing COM with LoRa fine-tuning, emphasizing the distinct advantages of COM's approach. The COM framework is designed to combine a large language model with specialized augmenting models, allowing it to perform tasks that neither model could achieve alone. This framework does not require updating the individual models but instead learns dense interactions between them through a few trainable cross-attention parameters. Our experiments consistently show that COM effectively utilizes the expertise from both models. Specifically, when combined with relevant augmenting models, the anchor model's performance significantly improves across various challenging tasks such as low-resource translation, reasoning, and code explanation or generation. Additionally, CALM is particularly beneficial in scenarios where proprietary data and knowledge are stored in parametric models. It can augment a foundational large language model with such proprietary models to extend capabilities in reasoning, world knowledge, and coherent generation over target proprietary domains. Future extensions of CALM could also be used to acquire distinct knowledge from multiple augmenting models. Thank you for watching.